Well, the work is named the NAUTILUS, an automated RESTful API vulnerability detector, and the authors are from Nanyang Technological University, Jianxin Group Corporation, China Industrial Control Systems Cyber Emergency Response Team, and the Institute of Scientific and Technical Information, China Academy of Railway Sciences. Well, first I would like to introduce the background. Let's start with the notion of the RESTful API. It is an established API standard extensively used for the web services. Indeed, it is a chosen standard for many mainstream cloud services providers. Well, about the notion of open API documentation, it is commonly referred to as the Swagger documentation. Basically, it is a standard method to document RESTful APIs, providing a uniform approach to describe the various aspects of an API and facilitating easier comprehension and utilization. Well, in practice, it is usually a preferred choice among the cloud service providers. And as shown in the right side of the figure, it typically includes the endpoint and the exact parameters to query them. So with all these foundation concepts established, let us dive deeper into the details of this work. Well, essentially, REST APIs are web services that use HTTP and provide an interface for the clients to interact with the service. So this means that the RESTful API services, they can inherit common vulnerabilities found in the web applications. So for example, they may suffer to the circle injection vulnerabilities, cross-site scripting, or XSS vulnerabilities, etc. Well, however, as of now, there neither has comprehensive understanding of the RESTful API vulnerabilities, nor has the specific solutions targeting for detecting vulnerabilities inside the RESTful services. So this presents a significant gap. And the authors of this work would like to answer, how can we efficiently identify and address these vulnerabilities inside these RESTful API services? Well, to answer this question, they first conducted an empirical study around two key research questions to understand the unique challenges of the RESTful APIs. Well, first, what are the categories of RESTful API vulnerabilities? And second, what are the differences between triggering the RESTful API vulnerabilities and triggering the bugs or internal server errors? Well, specifically to the empirical study, around 650 API-related CVEs have been examined, which mainly involves doing the statistics of the following two kinds of information. One is the vulnerabilities categorization, and another is the exploitation detail of the vulnerability. Well, one key finding is that the existing, the taxonomy of the existing RESTful API vulnerabilities can be divided into two main categories. One category is that the improper handling of the resources, and another is the improper handling of the user input. So for the former one, for the first one, it first can be divided as two subcategories, the access control and the privilege management. For the access control, it means that unauthorized users can gain access to the resources they shouldn't. And for the privilege management, it stands for the types of vulnerabilities where users can obtain higher privileges than intended. Well, for the subcategories for the improper handling of the user input, it can be divided as injection-based attacks and input validation. For the injection-based attacks, it is where the malicious input is injected to compromise the system, while the input validation is that where the system fails to validate or sanitize the inputs effectively. Well, in this work, authors have focused on the vulnerabilities caused by the user inputs and leave the rest type of the vulnerabilities as future work. Another key finding identified from the empirical study is that the RESTful API vulnerabilities are usually multi-API vulnerabilities. So what are the multi-API vulnerabilities? Essentially, these kind of vulnerabilities means that they cannot be triggered by only one single API call. Indeed, their triggering requires the execution of multiple APIs in a specific sequence. Furthermore, each operation within this sequence requires a distinct payload for triggering the vulnerability. Well, let's see a motivating example, which is simplified from an exposed CVE. Well, in this case, to trigger this vulnerability, an attacker needs to successfully accomplish at least 6 API calls in order. Well, specifically, the order first needs to create an account using the sign up API, and then did the login, and then sign in using the login API, and create a group and confirm the group's creation, and then create a malicious member inside the group, and finally did the validation to trigger the vulnerability. So you can see this is a chain of the vulnerability exploitation, which requires the user to accurately request each operation in this particular order, which is quite challenging for the traditional approaches. Well, inspired by this motivating example, the authors developed their detection tool, which named NAUTILUS, to automate the whole process. Well, the solution contains mainly 3 key steps. First, the manual annotation, and then the 2-stage testing, and finally the result handling. Well, in the first stage, the authors annotated the RESTful API documentation. Their annotation approach combines both human efforts and automated rule-based methods. Well, specifically, 2 levels of the annotations are added to the document. One is the dependencies between the API endpoints. For instance, in the previous motivating example, we remember that we need to first sign up and then sign in. So this is an API endpoint dependency. Therefore, specific annotation is added to declare that sign up should be called before login. Another level of the annotation describes parameter dependencies. Well, in the same example, we knew that the username for the sign up should be the username for the login. So an annotation of these 2 parameters will be added to claim that they should contain the same value. So the author designed some format or additionally added some requested fields inside inside the documentation to be filled by the developer, like of the testing targeted projects. Since they think that this does not introduce much additional efforts for the developer, since the developer always have enough project-specific domain knowledge, and the annotation only requires them to fill in several fields inside the documentation. Well, in the second step, the Nautilus performs a 2-stage testing. The 2 stages are exploration stage and exploitation stage. Well, the idea behind this is straightforward. In the first exploration stage, Nautilus searches for the effective testing sequences by first generating the test sequences based on the annotation, and then it dynamically validating these sequences. So these test sequences explored will be further used for the exploitation stage. Well, specifically, in the exploration stage, the Nautilus will first parse the annotated documentation to generate HTTP requests, and it will then query the target service with the request and records the outcome. Based on the dynamic outcome, it performs necessary mutation for the test sequence generation. We also, how does the Nautilus perform the generation and mutation? Well, mainly it has 4 strategies, namely the dynamic, success, example, and the random, as shown in the bottom table. What do these strategies mean? Well, the example means that the Nautilus will use the example value documented in the documentation, And dynamic means that they will use the values from the previous responses. And for the success means that Nautilus will use the last success value. Well, random just means random. Well, the key insight here is that if a request is successful, the Nautilus would like to mutate it further. And if it is not successful, the Nautilus will follow the documentation to generate a more standard request. By standard, this means that the Nautilus uses the example values provided in the documentation. So with the exploration stage, Nautilus further understands how to successfully query the target services. And then in the following exploitation stage, the values of these requests are replaced by the malicious payloads. So the content of the attack payloads are determined by the potential vulnerability types for that target, and the type is inferred by the empirically summarized heuristics. For example, if the testing sequence shows any sign of circle injection testing, Nautilus tried to use circle injection attack payload. Well, lastly, authors will manually validate the vulnerabilities and develop them as exploit. Well, for the evaluation, authors benchmarked the solution against the 4 SOTA solutions on the 6 real-world applications. The results were quite promising. As we can see, comparing with the existing solutions, we observe that both significant endpoint coverage advantage and superior vulnerability detection ability from the Nautilus. Well, for the real-world applications, Nautilus found in total 23 unique zero-day vulnerabilities, which are all previously unknown vulnerabilities, and out of these, 12 have been assigned with CVE numbers, and some of the bugs affecting the popular commercial services such as Azure services or Atlas cloud services. And besides, they also studied the contribution of the annotation strategy through ablation study. To do this, they had to compare the tool with no annotations, with only parameter annotations, and with only operation annotations, and with the full annotations. So the experimental result shows that both parameter annotation and operation annotation contribute to the vulnerability identification and endpoint coverage. Well, so this is the end of this talk. Thank you for your attention. If you have any question, please post it at the Slack channel, and the leading author will answer it. Yeah. Thank you.